Okay, I'm going to continue talking with you about the galactose and how the monosaccharide galactose that we ingest when we drink milk or milk products such as yogurt or cheese. Remember, lactose gets broken into two monosaccharides. One is galactose and the other is glucose. And so let's look at how galactose enters metabolism and how it gets converted into a glycolytic intermediate. So galactose, I'm going to write it in blue, galactose. And galactose, just like fructose, the first thing that happens to it is it gets phosphorylated. An ATP is used to phosphorylate it, and instead of going on the 6th carbon, it actually goes on the 1st carbon, so it's galactose 1-phosphate. And you can guess that it's a kinase that does this, and it's a galactose kinase. And I probably don't have enough room for that whole word, so I think I'll erase it, but you need to know that. And so the galactose 1-phosphate actually reacts with the UDP glucose, and we get an interesting reaction where these two join together, and one of the products is glucose 1-phosphate and the other product is UDP galactose. So notice that UDP glucose becomes UDP galactose, and galactose 1-phosphate becomes glucose 1-phosphate. And the enzyme that does this is called a transferase, and in fact it's UDP galactose, it's called galactose 1-phosphate uridyl transferase. Okay, so galactose 1-phosphate uridyl transferase. So this is a transferase that catalyzes this reaction. In one step, there's an enzyme called an epimerase that can change the UDP galactose back into UDP glucose. And this is a two-way reaction. These molecules are at equilibrium, and it's an epimerase that does this. So at any one point, if there's like too much glucose 1-phosphate and UDP galactose, the transferase can change them back into UDP galactose and glucose and galactose 1-phosphate. Or if there's too much UDP galactose, the epimerase can change it back into UDP glucose. If we need more UDP glucose to make glycogen, it can go that way, or it can flow back to the glucose 1-phosphate and to the glucose 6-phosphate. And I'm just going to highlight the glucose 6-phosphate by circling it, because that's a glycolytic intermediate that the galactose is changed into through mainly the pathway of glycogen synthesis from glucose 1-phosphate. Now let me point out that phosphofructokinase is the key regulatory enzyme of glycolysis. And the reason that the first enzyme, hexokinase, is not the key regulated enzyme is because phosphofructokinase is the committed step of glycolysis. The reason for that is that the first step, hexokinase, makes glucose 6-phosphate, which can either be used to change into glucose 1-phosphate and all the way to glycogen, or it can go down glycolysis and be changed into pyruvate. So hexokinase is not the committed step of glucose atoms. They have at least 2 different fates, and in fact there's a third fate too, where I probably shouldn't use red, where they change, where the carbons can go to the pentose phosphate pathway, PPP pathway. So again, glucose 6-phosphate is not committed to pyruvate in glycolysis. It can go 2 other ways. So the committed step is really the phosphofructokinase, the third enzyme of glycolysis. Other interesting things about galactose, eating galactose, is this transferase that allows galactose to enter the glycolytic pathway. If it is not working right, or if it's absent in a human, it causes disease called galactosemia. And galactosemia causes infants to not thrive at all. They have all sorts of problems, and including mental retardation. And that transferase is super important. If we don't have the transferase, the galactose will, our bodies will try to get rid of it one way or another. It'll show up in our urine. Blood sample will have very high levels of galactose. Our bodies will try to change it into galactitol, which is the reduced form of galactose. And galactitol can also cause problems. For instance, in eyes, in our lens of our eye, the galactitol, it will start to cause water to flow into the lens, which will cause a cataract. And so young children with galactosemia will have cataracts. Also, in Northern European countries and in the US too, Anglo-Saxons will be able to continue drinking milk a long time after into adulthood. Usually in most parts of the world, when people are weaned, when babies are weaned and young children stop drinking milk, they lose the enzyme lactase, and so they're not able to metabolize lactose into galactose and glucose. And it turns out that in Northern Europeans in the United States who do continue to drink milk for a long time because they do have lactase, they tend to get cataracts more than other people who don't drink milk. So I just thought that was interesting, an interesting section in your book. And that will be it for this section.